All right. Hi. Good to see you again. Um, the agenda for today, we finished the example we talked about yesterday from first order logic. And then we transition into a general discussion about reasoning with respect to availability of facts in knowledge base. So we will talk about two different alternatives there. So basically, where we have a complete set of facts. So what kind of reasoning we about a phenomena or about a domain that we want to reason, what kind of reasoning is applicable there, versus a case where facts can be added continuously and you don't place any assumptions on the completeness of your knowledge. And this is to kind of motivate a need for reasoning on a global scale when you do not have capabilities to verify consistency of your facts or your rules about a certain domain. And that will be an introduction to a challenge for representing real knowledge to be applicable for reasoning. So that will be the focus of today and next few classes, as well as the focus of Lab 3. So I promise you to return to this example. We considered it yesterday. So just to remind you, the input to the task is the sentence there on top of the slide. And the task is, the assignment is to interpret the sentence written in first order logic syntaxes. And again, so in a fast forward manner, so well, again, so when you see such task, for example, in quiz or so, then don't try to interpret it verbally or mentally. Don't do it as a mental exercise. Rather, I approach it formally by simplifying the sentence. And so what we finished at, or I mean, the previous steps for this was to apply the negation of the universal quantifier rule, which stands so the equivalence is that not existential quantifier formula is logically equivalent to existential quantifier not formula. And so the important thing, once again, that I will not go far from the microphone. So is that the quantifiers are applied on all on the part of the formula which includes the logical variable. So in this case, I is present here, and so as such, the universal quantifier is applicable to the whole formula. And then we turn it in the first step into existential quantifier, and then did elimination of implication. So between these two global parts, I mean to the left and the right part, and remember this equivalence for the future. And now we, or yesterday we ended up at a case where now we substitute this existential quantifier, so after this implication sign, into the main formula. So like this. And the rules that we will apply again to remember quantifier negation rules. So the first one I indicated before, so it's and we talked about it. So not I for no I is logically equivalent to exist I such that not formula I, right? There is another one, and that was basically I omitted yesterday, and it's essential to solve it. So the other way around. So negation of existential quantifier on is logically equivalent to um, universal quantifier I for all I not formula. So this two. Hmm? So now we have this equation for not I, and just to maybe to put it on the same page, no, we will summarize it all at a later stage. So let me just put it like this. Remember. So this not y then is not all I not not a formula which is on J floor and not IJ. So okay. Mm, yes. So now what do we have here? So this is the Morgan. So that's we write not for all I on So now I need to be careful. Oh, no, yes, J. Floor. Or touch. Hmm? You you should protest. So one thing.
It's on negative.
Huh?
Why is on negative?
No, it's not that one. So the thing is, so here, uh, so this is, let me see. So this is why. So this is why, right? So we are doing not why. So here, not not no, sorry, not existential stuff. Then, so not existential. So that's rule number two. So not existential is equivalent to universal quantifier not formal. So I have one more note which shouldn't be here, basically. Are you with me now? No, look. So this is not y is not exist j blah 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 blah. And that whole thing, so together, so if you take it with two, together with two, like this, is translated to universal quantifier not formula. So universal quantifier not formula. So now this not uh, um, and um, and the end statement. So using De Morgan law here, this one is equivalent to not first term or second term. So, and that is what is written here. Now, so if you look now at this construct, so it corresponds. So the logically equivalent is the implication. So this also can be written as on to be straightened on J located on floor implies touch I J. Correct? We are here. Implication elimination, or it works both ways. So this is the final form, what we want to achieve when transforming the sentence above for not y. So now let me write all together. So what it will be. So it will be an existential I where the first term will be on I table and then the modified equation for y. So final form. So there exists I such that on I table, and now we write this y for all j such that on j floor implies such put it on implies touch ij. So this is our final form which we can interpret. So can you help me interpret this rule linguistically and using language? Just read it kind of from left to right. Give me some variants.
That there is a table and it's always touching the floor.
No. I is a thing on a table. Object on a table.
That sits on a table that's always on the floor.
No, that J is also object.
Okay.
So there is something on a table and something on the floor. And for all on the floor implies that it touches something on the table. Try not to make sense of it. Just read it through. I mean, that's what I'm saying. I mean, that's one kind of message, important message. Using syntaxes, you can make any kind of statement. I mean, logic doesn't mean that. I mean, whatever you write, syntactically correct, make sense under certain assumption. So this is just a statement. Then it can it can be evaluated as true. Then whether it makes sense or not, it depends really on how this rule appears in the system at all. So basically, what it says that there is an object on it that is on a table. So amongst all objects on the table, so there is one on a table that touches all the objects on the floor. I mean, it's a nonsense. So if you think about physical world, unless you have drilled a hole in a hidden dimension. But it is a syntactically correct sentence. So and again, I mean, So there are two reasons for choosing this example for me. One is that to demonstrate that you need to apply the logical inference rules to come to certain conclusions. Because I mean, in the way how it is presented, also syntactically correct. You no, I mean, you hardly can interpret it. On the other hand, so we came to a conclusion that this sentence described an impossible situation, which has two consequences. First, I mean, such rule can appear in the system. Then maybe there is a need for extra checking that rules do not contradict to certain facts. But without but in order to do this, you need also some default relations or exceptions saying that items on the floor can never touch items on the table. So without this explicit relation, so the system will just interpret whatever it has. So it just whatever is not forbidden, so it is allowed. And this is an example of something which is called monotonic reasoning. So monotonic reasoning for an open world assumption. So, and that's what we will continue with now. Or rather, we start with a non-monotonic case. So let me check if you in Zoom you see my screen, the main screen. Yeah, that was correct. It's like yes. Do you see my main screen? Yes. Okay. Good. So basically, we come to understanding that there could be logical systems or systems which require reasoning can be built differently with respect to how you organize your facts, storage of facts. And there are actually two alternatives here. So you either assume that the domain of your interest is completely described by the set of rules. So whatever is written there, so is true, and if it is not written as true, then it is false, basically. And the second option is that you do not have, well, you relax this assumption, so that just not knowing something doesn't mean that it is impossible. So, and that was one of the examples with classical first order logic. So without having some extra information about relations of things being on the floor or on the table, you just accept whatever system gives you as an answer as a result of logical inference. So the first case, when you assume that everything is prohibited while not explicitly allowed is called a closed-world assumption, CWA. And it is about, well, facts keeping being present in the system, but also rules, default rules that have to be compliant with. And the logic should always resort to the rules it has. So if, for example, there is no rule saying that Mary loves John, so it is assumed to be false. And then you need an extra mechanism, of course, I will talk about it, to keep these rules consistent. Examples of such systems are classical expert systems, which are used for diagnostics, like in medical domain, law, legal expert systems, autonomous vehicles. So it is where the decision should be taken under the current assumptions, not allowing, so basically leading to some deterministic conclusions. However, in these systems, so new facts appearing as the system functions, they can invalidate old facts. So here is a simple graphical explanation. So you describe same person at different stages of life, and so the new skills obtained with age partially or completely invalidates the old information about what a person is capable of and how it acts. So the reasoning or inference in non-monotonic reasoning systems is well, includes facts, as I said, and a set of default rules. And then these rules are applied synchronously, or there is an algorithm that's kind of a search algorithm that kind of applies all rules sequentially that satisfies a given start condition, start facts. And at any step, you use these default rules to proceed to the next reasoning step, and until you end up in a certain conclusion on which these default rules agree. And then again, so these rules are not static. So whenever there is a change in the domain of interest, so the rules need to be updated. So and that normally that can be detected by, for example, contradiction with known facts. So in addition to inference, just like a logical inference, so just checking logical validity of certain rules. So non-monotonic systems include mechanisms for revision of facts and rules, which is like belief revision, etc. So you can find more information about it in the book. As for the reasoning, so again, as a simple example, so one can you can trace offline. So here is a linguistic form of a story describing some default rules, how different actors or entities interact with each other. So some love triangle. And we have facts, some atomic facts that we encode. And so now we want to make, and that is what we have. So that this is all the knowledge we have about the domain. So maybe I now will go very quickly through the reasoning, just pointing out which rules are applicable at each step, and just to demonstrate the idea. And I won't show the process of revising these rules, but the idea is that in addition to facts, encoding of facts, and this syntax is describing forming of sentences. So this is the rules that you have. So if you can check, rule 1 corresponds to the first sentence. So Mary, and P4. No, P4, don't use and Pete. Oh, sorry. And no, P2, then P2. So not P2 what? And Mary is not in love with John. So the rules tells that she will love. So that will result in positive P2 in true value. Again, so you can decode these sentences and check validity offline. So and the reasoning starts with some initial state of facts. So that's an input to the system. So that comes from just description of a current situation. And the reasoning itself, the non-monotonic reasoning, is about checking so the initial state of facts against all the rules in the system and applying them, well, sequentially, but here they applied, so this transition, when you will read it at home, shows the final result of applying, for example, these three rules. Eventually. So then you do it in iteration. So at each new step, so you take the current inference result, and then again you check which rules are applicable to it. And in few steps, you basically arrive to a final step, to a terminal state, which can be interpreted like this. So for a given set of starting conditions. So John doesn't love Mary, Mary doesn't love John, Mary is a friend of Pete, and John is not abusing Pete, and John is not in a bad mood. So, and then, so the result of the reasoning, it can be different depending on this initial state. So you can check again for a different initial conditions that the result will be different. Which one? Well, check it. But once again, the whole idea is that with non-monotonic reasoning, so you start with a set of facts that you through which you describe a current situation, and your inference is governed by the rules that are defined in the system. So everything outside, everything outside these rules are impossible. As I mentioned before, so it is super important for such systems is to have these rules consistent. And this is done via a process of belief revision or management of assumptions. So it is this part which is dynamic. It reflects the dynamics in your target domain. And well, while being very useful in many practical applications, as I mentioned, autonomous driving, expert systems, the main challenge with this type of reasoning systems is the complexity. So the inherent complexity of maintaining the consistency of facts. So revising the beliefs. So the larger is your base of beliefs, rules. So at the end, you end up in a computationally hard problem of keeping the consistency with every new appeared fact. Is there a use case for other type of reasoning? So when, I mean, similar to what we have considered, so which do not place any assumption on some default behavior. So it doesn't use any belief. So which is, in other words, are called monotonic reasoning systems. Well, there is. In many cases, and you want to reason about very large-scale systems in which checking the consistency of all facts and all rules is infeasible. So, like in which again, so it is easily possible some correct, but maybe not very meaningful sentences. So apparently, yes, we talk about like internet scale reasoning. So where we have lots of information to reason about, and where we do not but where it isn't feasible to do this kind of sanity check of facts. And this type of system is also called open, so systems with the open world assumption, or the OWA. So we're again putting it verbally, so everything is allowed to, if not explicitly prohibited. Right. So examples of systems that do this kind of do reasoning using open world assumption, or in other words, monotonic reasoning, as I said. So these are classical logics as we consider it. Just plain classical logic. And so again, monotonic reasoning, you can get an intuition by a kind of a discovery-driven inference. When you do not kind of you rely on the truth of already discovered facts. So so the new facts do not invalidate the previous one. So whatever facts you have in the system, they are taken into account. But then the question is whether it makes sense to use such systems in changing environments, where, if you remember this case, and I mean, this case makes sense, makes a lot of sense. because I mean all practical environments are changing dynamically. So so new skills are invalidate the previous one. So this problem is addressed by monotonic reasoning systems by separating the episodes. So we split the lifetime of system on different time intervals and reason within each time interval consistently. So we do not do any revision between the walls. In practice, what we need hybrid systems. So we need systems that do this type of logics that are not accessible via this type of reasoning, which is not accessible by classical logics, like reasoning by default. So best, simplest possible explanation to certain facts, which does believe revision, and at the end, so it is more explainable, while also having formal reasoning that guarantees logical deductions like classical logics. So basically, the current development is happening within the hybrid case. So maybe, so I see the clocks now are 40 past 1. So maybe we take a short like stretcher and then continue with the focus scenario. Yeah, so let's take 5 minutes break. Recording. Yes. So now, I mean, in what follows, I want you to focus on this on an example of a large-scale distributed system. So, like, I mean, connected to digitalization in a general sense. So we want to automate certain aspects of our life, and so. For example, we use a telephone. So behind a telephone, so there is a great deal of infrastructure, and this infrastructure, so in addition to telephones, obviously include base stations. So base stations, it's complex objects, so they have different functional units that interact with itself. On the other hand, you have mobile operators, Telia, Comviq, whatever. So they use these devices somehow. So they want to provide service to you. So, and of course, since it all works smoothly and seamlessly, so it means that, I mean, these different pieces are tightly integrated and they are interoperable. But it is, as you understand, it's not a monolithic block. So you want to make a system where you can with which you can reason, basically. So with which you can test whether where a certain unit is compatible with other units to deliver certain functionality. And so we will focus on a real use case when on which you want to apply certain logical inference. And this logical inference, it won't be about finding, items on the floor, touching items on the table, of course. But I mean, this inference will have a very pragmatic output. And this or serve very pragmatic purpose, and this purpose will be different depending on the actor who uses this system. So it should. So this system should allow a user to interact with the system in some way. System architects, administrators, and even business planners. Again, a scenario which is kind of somewhat close to me, again, in the case of mobile networks. So what, from the mobile operator point of view, or from the user point of view, you probably want to say, so I want such a subscription that allows me to run, to control remote robots, with a certain delay. Delay which is limited to a certain value. And the business unit say, yes, and you specify how many robots and such. And the business unit obviously need to provision the network in such a way that delivers this service to you. And you talk still on a very high level on terms relevant to contract negotiation. So I just want this service, I want to pay this much, and the business unit should match it. But then, so this request should be translated to some technical requirements. Technical requirements should be translated to a particular configuration. And in principle, you want that all the system works completely autonomously. So it's a self-management managed system. So what is needed for this? So before you come really to the inference part. So you need to describe your environment. So and again, here we talk about a global scale. So you do not you are not restricted to a certain domain. So now I just want to formulate, give a general formulation of a problem. So you want to be able to describe different objects that are needed for composing a specific functionality. How to describe it? So you as a one who create query to the system, want to understand. So what each particular, so not only name an object as we did before, but you need a description of what it is capable of, or at least you should be able to understand how you can use it for your purpose. And on the other side, so each resource should match this demand by providing a description of its capabilities. So what am I capable of? So description of resources is essential in this case. Because, as I said, if you have this proper description, you apply logic, inference, you can, altogether this can be useful in various, in numerous tasks, like decision making, fault detection, and others. So self-management, as I mentioned, as such. So what we will be focusing is how, if you think about it, it's a challenge. How to describe objects, so different kinds of objects in the world, such that on the one hand you understand how to use them, and on the other hand you can describe your own capability so that others can use it. So we will talk about how to represent meaning before we can apply any logic. And so we used the word semantics in the context of classic, this simplest logic, propositional logic. So in that case, I gave a definition that semantics meaning assigning meaning to symbols. So that was the kind of simplified definition. But here we extended to general understanding of semantics, just assigning general meaning. So what does it mean? So in this very example, very simple and illustrative example, so two people want to negotiate and agree on certain meaning. So let's scroll fast through this scenario. So and here the important thing is that so this is the way it is communicated, right? So over a communication channel. This is the actual content of what is being communicated to the final destination. So the problem of assigning meaning, or the problem that appears when we do not assign meaning, could be that understanding of the same message could be completely different. So in this case, it could be like completely different understanding of a situation, assigning to exactly same message. And then, of course, I mean, one and the same entity or phenomenon can be described in multiple possible ways. So it's, I mean, yeah, well, in the case of natural language, so it is ubiquitous. So you can express it in many different ways in different languages, but still, so the meaning could be exactly same in all cases. And again, so the communicated information could be translated from different languages, have different interpretations, but at the same time, again the semantic content can be same, and yet different between the communication parties. So what is the problem? The problem is how to link, or actually there is a need. So what I want to demonstrate here is that there is a need to link somehow communication, the way how you communicate certain things to the semantics, to the meaning of what is being communicated. So you need to do the, and this is hard if you think about it. So and forget about this last bullet point, LLMs. So think about how to whether it is possible at all to have this kind of registry of all messages and somehow description of situations. So that's hard. So and again, so I mentioned LLMs because it appears to be it appears to understand in whatever languages you speak, but again, so it has some internal translation. So in addition, you need to link the same meaning to different communication channels that you use, or encodings, so to say, of these meanings. And that creates additional complications. So if you think about all possible variants. However, what you can do You can instead of trying to make a link to kind of the protocol in which you communicate and somehow describe the semantic content of it, you can formalize the representation of the situations and the objects and the relationship between objects describing the situation. So in this case, what I mean is that if you have the standardized way of representing knowledge, you can just explicitly communicate it. So you remove this ambiguity of message and the meaning. So what you want, you want to create a technical system that communicates meaning. So formally describes and communicates meaning. So, and in this case, as you can understand, so if you have a formal description of your intent, so that's a kind of one of keywords in this domain. We will not go into this agentic domain, so to say. But this intent can be uniquely interpreted. So, or it should be uniquely interpreted. So that is our target. And then in this case, you can find so having your own kind of description of needs, so also presented in the same formalism, you can match it to the presented capabilities and decide and solve the compatibility problem. And let me maybe first show you this slide. And this formulation appeared a long time ago, back in the beginning of 2000. So in early 2000 years, where the vision was to enable more data-driven search in the internet. So the internet has grown to that time. It has grown to well, to significant size. However, it was still kind of set of linked web pages, just kind of mechanical system linking web pages and allowing to retrieve, just jump between the pages by hyperlinks. So the idea was that, of course, there was an understanding that internet is more than that, and why not to be aware about the information that is linked. So you want to link you want to link information and make a system that reasons about information that's that is linked. So basically, there was a vision which was resulted in a technology which was called semantic web, where everything would be or all data kind of presented in the internet would be connected by relations. So the web pages won't be just text documents, but rather so it would be possible to understand the meaning of the information. And as such, so looking a little bit ahead, I can tell that semantic web is dead. That's bad news. Or well, simply because of scalability problems. But it is that as a kind of global vision. So that I probably in one of the upcoming presentations will show you methods which were, or tools which were thought to be used when creating web pages. When you while creating a web page, you can also introduce semantic annotation to, for example, when you describe a story about yourself, so you can link to different descriptions of objects that you're describing. So this never happened on a large scale, and the idea was again to enable more semantic search. So which is now kind of implemented via Google, via LLMs and such, but using its totally different concept. So here the idea was that explicit encoding or representation of information that will be the key to enable this kind of meaning-based search on the internet. So that didn't happen. But it was very hot topic, and so the benefits was really clear. So the problem was formulated with relevance way beyond the internet. So as I said, the problem was to, in the first place, enable. Oh, sorry. Oh, I should have this scenario. So we want the different heterogeneous resources to interact, and we want to be able to reason about this. And this goes way beyond the World Wide Web. It is applicable in smart industries, in general industrial automation and such. So there was an interest from big industrial players, and there are plenty of researchers, engineers working on development of the semantic technologies. And as a result, several standards appeared, and which are used as of today, so actively used in the domain of management of complex systems. So if you think about, for example, smart industries or industries of the future, so these tools that you will study are used there for sure. As I said, in telecom world, the tools that we will consider definitely used to describe interoperability of a system for reasoning on faults, etc., and overall achieving this zero touch vision, so that the systems should be managed. So let me just skip this stuff. So what is left of this semantic web vision is really a set of tools for which are heavily used for resource integration. And what are these resources? So as I said, so they were developed in such a generic way so that their applicability goes way beyond pure web resources. So everything, so all objects like in the physical world, in the digital world, can be annotated using these tools with a kind of single purpose to create a system that is able to reason about their integrability and compatibility. Behind semantic technologies, semantic web technologies, there is a more generic concept, which is known as knowledge graphs. So what is knowledge graph? Knowledge graph, well, it's a combination of techniques. So partially it can be seen as a database because you can insert queries. So it is like a database. You will try it yourself, and the system will answer. The difference is that how the data is organized. So it is organized as kind of as a linked graph structure, which bears formal which has a meaning. So so the graph connections reflect the meaning of interaction between different entities. So again, mechanically, so you what we want to do with the semantic description, as I said, to transition from linked from hyperlinks to data links, so where you can decide on logical or semantic structure of the presented information. So again, what we want to achieve is that a web page is not just a kind of a simple HTML document, but rather you can reason on belongingness, for example, or in the hierarchical structure of the knowledge, which is presented in the text. So illustrated here. Where I mean, whether the question is if we have real systems following this linked data concept using the tools that we will consider and available for reasoning, yes. So I don't know how many of you have used it so far, but I mean, most likely you everybody use Wikipedia for searching facts. But on a side, there are two other projects, which is called DBpedia and Wikidata. Did you see this before? Well, there will be at least something new. So this is a DBpedia. Again, so it's an HTML document, and behind it, so basically, it's a semantic description of the information which is presented on the corresponding page of Wikipedia about Stockholm. So if you go to so there is a text with links and such. So the knowledge which is described here with all this hyperlinks and text is formalized in DBpedia, and also Wikidata. So it's slightly different projects focusing on different aspects of annotation. But the thing is that you can see it first as a proper database, so describing the information with different fields, so you can do queries to it. So I will show you query tools. But then you can also perform certain reasoning, as you will see. And again, so today I will start introducing you the framework for describing this knowledge. So whatever you see here, again, as a HTML document, so behind the scene, so there is a format, there is a language and a framework for representing data and linking data. So let's see if I'm not sure let me ask if you see my screen again in Zoom.
Yes.
Okay, good. The main tools that basically behind more advanced tools are two. So we will overview them all tomorrow. Today I will start introducing RDF. RDF is very simple. So they are all standardized. So you can find the API to these languages on the internet. So today we will be talking about resource description framework and see the transition to RDF schema tomorrow. So again, essentially what we want with the resource description framework to be able to annotate knowledge. So they relate to annotate the objects, their properties, and the properties can be relations, properties can be values, and all in all, when we do this annotation, so you can scan them all and build a knowledge graph. And understand how they all connected. So resources. So the first keyword in RDF is resource. Resource can be anything, like virtually anything. Web page, XML element, a collection of pages, and further on. So it can be physical objects and such. In general, a resource is just anything that has an identity. And identity again, so that is where this all this framework for resource identification stems. Actually, that you know. So you normally use URLs, but URLs are just subset of uniform resource identifiers. So it's a standardized way to name resources. So that will be used. And then, as I said, so, we will describe resources via their properties. And so property can be a value. So like, for example, age, like a particular age of a person. Or property can be in relation to another resource. So what do I mean? Again, I'm using the case of web as, I mean, this is the main use case behind semantic web, but I mean, you further can generalize it to other scenarios. So the important kind of distinction. So we have objects in the world, like a web page. It's just an object. And then, so this object describes is a description of different resources. So there are references between objects. So how to transition from one object to another. So that's a kind of mechanical stuff. But then what I want to make you kind of for yourself distinct is we are talking about describing meaning of the information presented here. So we will be talking about identifier of a resource that is presented somewhere in a physical location, and annotating its property that it's so this person is employed, and again, the place of employment, so the identification of this place is presented on some physical object in form of a web page. And then you can kind of nest this description, this idea, and so you can describe the whole web page itself as a resource and how it relates to other web pages. So everything we want to represent everything in a unified using the unified description framework. So to have a complete ecosystem. So the basic construct of resource description framework is very simple. It is called a triple SPO triple: subject, predicate, object. So all knowledge at the end boils down to a list of triples. Triples. And only when kind of doing extensive parsing, so you can kind of unroll it to a graph. So, there are connections between these triples that at the end altogether form a graph. At this moment, you should think about triple as kind of fill in a questionary form. So you have a subject, a resource. You have well, property, again, a predicate, and a value or an object. So subject, predicate, object. So these are the object can be different types. So it can be literals, it can be numbers, like in this case. It can be other objects identified using unified resource identifier. So in this way, we turn data into actionable objects, so you can really make sense of what is represented in otherwise textual form using special algorithms that understand, okay, so this is a source identifier, so if I go there, I understand its properties, and then I can do whatever reasoning I want on it. So I will finish at this moment just presenting a quick summary. So we are about describing resources and concepts and how these resources depend or interact with each other, in what relations they are included. And for this, we need to have several fundamental components. So a resource, we need to identify a resource. Resource can be anything. So, like for example, it can be a human. So we essentially want to create a formal system that uniquely or disambiguates the language, so that machine, when reading it, can uniquely understand the meaning of this resource and what it does. So basically, out of all possible instances of John, so we need to therefore identify a specific one. And this we do with explicitly given identifier of this resource. The same goes for the object part. So again, we do identify it, and then importantly, we also need formal description of the predicates, of the properties. And as you can imagine, they also can be many. But now, I mean, at least we agreed that we will formally define it somewhere. But we just need to indicate in what part we need to take a description of the meaning of the predicate. And so this, looking a little bit ahead, so this description, formal description, are called ontologies. So it's, well, formally defined properties. So again, properties with the same name in different ontologies can be defined differently, but that's fine as soon as we just disambiguate them by giving proper identifiers. So where a computer can or a program can go and just parse all the necessary fields that are relevant for matching to its demands. So tomorrow we will go into details of RDF and RDFS. Yeah, and in the next module we will talk about ontologies and reasoning on ontologies. Okay. Any questions? Okay. See you tomorrow. And goodbye to you in Zoom.
Thank you. One more question, actually. Could you also share the slides in the record?